Everybody, and welcome back to another fun and exciting geometry class. Today we'll be getting into lesson 5.1, and we're going to do 5.2 in the same video. You may be looking and saying, hey, the background is different, and maybe you look different. Well, it has been a while since I last recorded from chapter 4, so I guess it's been over a year since I recorded, so we've got the remodel done on the house, and maybe I've got some more gray in my beard or something, but it's been a while. So for you, it was like, yesterday. For me, it's been about a year since I recorded this geometry lesson. So I haven't forgotten how to teach, okay? So I still remember how to do that, but it has been a while. So let's go ahead and jump into it. If you will, look down in your book on page 234. I like that page number. And we'll be doing lesson 5.1, surface measurements. So now what we're going to do is we're going to be transitioning kind of away from the proofs and different things that we've been doing. And some of you are like, yes, finally done with the proofs. I know. And we're getting into the type of geometry that maybe you thought geometry was all about at the beginning. We're going to be doing area and circumference and dealing with those types of things. You're going to be learning some formulas. Some of those formulas you already know. Some of them are going to be new. Some of them we're going to be doing just a little bit different way than we used to do. So that's what we'll be doing here, is kind of jumping back into some of the things that you thought we'd be doing all along, like area and circumference and things like that. So let's jump into it and talk about, what does a surface measurement mean? Well, surface measurement just means you're measuring the surface. Remember, we're in plane geometry. We're not in three-dimensional geometry, so we haven't learned about volume and a lot of three-dimensional shapes. We're learning plane geometry or shapes that fit on a piece of paper, right? Not things that are like boxes and cubes and different things like that. We're learning about squares and circles and rectangles. So when we're talking about surface measurement, we're talking about measuring the face of an object. Like if it's a three-dimensional object, we're just measuring the face of it. We're just measuring one side of it. So when we're talking about that, when we're talking about surface area, any plane shape can be measured by the number of square units it contains. Even a circle can be counted up, or it can be measured by the number of square units. And you say, well, how can a circle contain square units, since a circle's a circle? That's not really a circle, but it's close. Well, what it is basically you're on this grid, okay? And there are ways that you can figure out, and so you might be looking like, okay, like look at this one right here, where it's kind of like just this little piece of this is part of the thing. How do we figure that out? Well, there's formulas that can tell you how to figure that out. But when we're dealing with these plane shapes, we're dealing with this concept of like a shape, a circle, a square, whatever, on a grid, on a square. So these would be what's called square units. So each one of these, you could say like this is 1, 2, 3. Obviously this is not 4, because that's like part of 3. So you can count the main ones. You can count the ones that don't have the curve of the circle in them. But how do we count these? Well, we're going to need a formula to count those. So here's a key, though. Remember that it's always in square units. All of these are going to be square units. So square inches, square feet, square whatever we're dealing with. And sometimes when we don't know, we're just going to write u squared. And you'll see that in your book there, where they write u squared. So they don't tell you the units. We just have to say units squared, since we don't know what the unit is. All right, so equal figures. This is on page 234, about halfway down. Equal figures are plane shapes with equal or equivalent area. So in other words, they don't have to be the same shape. So I've got a rectangle here. Let me move it real quick so you can kind of see it a little bit better. There we go. So there's the rectangle. Now, you could obviously draw another rectangle next to it that's exactly the same, right? It would be called congruent. And we've talked through that. We've proved that. We've done different things with congruent shapes. And then we could also draw a similar shape, maybe a shape that has the same ratio, but it's smaller or larger potentially than the shape we have. Now, with equal figures, here's what we're going to do. We're going to make a plane shape with equal or equivalent area, but they don't have to be the same shape. So let's think about this. Let's draw, because I think you remember, like when we cut this with a diagonal, basically what we've done is this is 1/2 and this is 1/2. We basically cut our shape in half. So what we can do here is if we cut it in half, what happens if I make my triangle continue over here? So I draw another half of this triangle out here, right? Well, what I've done is I've created this purple triangle right here, right? So this purple triangle would be the area of it, since this is 1/2. So let's just come up with a number. Let's say that my rectangle equals 81 square units. So units squared, we'll do it like that. Well, my triangle is also going to equal 81 units squared. Now, the way that we know that is because this is half, and then this would also be half out here. It's almost like we take this piece right here and we just rotate it over here. We just kind of flip it over here. And what happens is we end up with the same exact area. So when we end up with the same exact area, that means that these are equal figures. Now, they don't have to be connected like this. They just have to be equal figures. Theoretically, and it gets a little theoretical, but you could have a rectangle that had the same area as a circle. Why do I say that's theoretical? Because all circle areas are done in approximate. So, you have because you're multiplying by pi, 3.14, 159. And so it keeps going on, and the decimal never stops or repeats. So we have to approximate pi at some level. So when you're dealing with a square or a rectangle or a triangle, it doesn't have that same curve. So you could get really, really close, but you wouldn't necessarily have an exact match because you'd have to round off at some point. So let's go ahead and look at the next lesson there. There's a lot more there in that lesson, like you can read through it, but most of it is just things that we will kind of hit as we go on through the rest of this chapter. So jump down to 5.2. This is on page 236, and look at Theorem 68. Theorem 68 says the area of a rectangle is equal to the product of its base and its altitude. I don't know why they say base and altitude and then give you h there. So I don't like it. So let's call it base and height. All right, there we go. That kind of matches with the h that they give you there. So they say altitude and then they give you h. So I don't like it. So we'll say the base and its height. So this is the formula that in 8th grade, 7th grade, you were doing this formula like A equals LW. Right? So the rectangle equaled LW, length times width. Well, we're saying the same thing. It's just that we're calling these something different. Well, in fact, let's kind of put these together. So the A for area is now a capital letter R. So when you're using capital letters in your formula, this means area of a rectangle. So capital, that should be a T, means area of. And you could have area of a circle would be capital letter C, area of a triangle, area of a square, area of whatever shape, you use the capital letter. So if it's a triangle, you'd use a capital letter T, and that would show you your area. So capital means area of. So we have an area of a rectangle is the length, and now we're just saying that the length is, now we're going to call it the base. Okay, we're just changing the name of it. It's the same thing. So if we draw a rectangle here, this would have been the length back in grade school, but now we're going to call this the base. It's the same thing. We call it the base because it's sitting on the base, right? That's what it sits on. And then we have, this used to be the width, and now we're calling it the height. And that makes sense, right? Because it's the altitude, or it's how tall it is. It's the height of the rectangle. So we're going to use this, R equals BH. We didn't change the formula at all. We just kind of put different letters in there to represent the same exact thing. So easy formula. You've known this for a long time. R equals BH. All right, let's look down here at corollary 68.1. Two rectangles are to each other as the product of their bases and their altitudes. So here's kind of the concept here is that you have two rectangles, and they don't have to be the same. You know, they can be very different, but their areas are proportional to each other as their bases and heights are proportional to each other. In other words, we'll call this the R, and we'll call this one the R prime. Okay? Now, these two areas are to each other, or in other words, it's proportional based on what? Okay, so what makes these two things equal or proportional? Their base and their height. So over here you would have the base prime and you would have the height prime. So base prime and height prime. If you take these and if you multiply these together, basically, and you find out what is the area. Let's say that the area of the first one is 12 and the area of the second one is 10. So the base and the height in this case are going to equal 12 when multiplied together. So it's going to be proportional because it's just kind of breaking it down. This is almost like factoring the area out. So let's say that the base is 4 and the height is 3 in this case. That gives us our 12. We'll say that the base is 5 and the height is 2. Okay? So here's what happens when you multiply this together. Obviously, you get 12 and 10. So these two are proportional to the area of the other two. And it just, hopefully it makes sense because, right, it's the formula. It's like saying the area is proportional as the formula is proportional, or as the parts to the formula are proportional. Okay, let's look down here at 68.2. Two rectangles having equal bases are to each other as their altitudes. Now this one's a little bit interesting because we have equal bases now. So we have bases that are identical. So this one kind of looks like, remember the mean proportionals that we did where we had A over B equals B over C when these are equal right here? So we're going to have the same thing right here. So this is what this proportion is going to look like is we have like the altitude over the base equals the base over the altitude prime. Okay? So these, when these are equal, you end up with a mean proportional. Let's look at what that looks like with actual, rectangles. So if you have like this guy right here, and this has an equal base, but the height is different. So these bases are the same here. However, in the other one, we're saying that was base and base prime. Technically, it's still base and base prime. But you're dealing with, in this case, you're dealing with a different size shape. You're not dealing with equal shapes. You're just dealing with equal bases. So it's a little bit different. So these shapes are not equal shapes, right? This first one is a lot bigger than the second one. But that's fine. We're just dealing with the equal base here. Now the height is going to be proportional based on the fact that the bases are equal. So two rectangles having equal bases are to each other as their height. So in other words, this R here and this R prime are going to be to each other based on the height because the bases are equal. So it's going to be based on the height. They're going to be proportional to each other based on the height. That's what corollary 68.2 is telling us. All right, corollary 68.3, two rectangles having equal bases and equal altitudes are equal. that kind of makes sense, right? So, if we have an equal base and an equal height, so base and height, and those are equal, then you're going to have the area is going to equal the area. So you're going to have, this is going to be like congruent right here, right? So if you ever end up with ones that have equal bases, equal heights, then they are going to be equal. All right, 68.4. The area of a square is equivalent to the square of its sides. Again, this should be something that you remember from grade school. You should have learned, probably in grade school, you learned A equals S squared, or A equals S times S, or something like that. So really this stays the same. The only difference here is now in geometry that A becomes an S, capital SQ. So just make sure you remember with the square, you actually use the SQ, not just the S. It avoids confusion with other shapes and just with the small s itself. So SQ equals S squared. You should know how to do that, but obviously if you have a square that's 7 on all sides, you could say 7 times 7, length times width, base times height. You could do that, but it's the same as saying 7 squared because they all are 7s, so it doesn't matter which one you use. Might be just a little bit faster. Either way, it's the same thing. All right, so that's corollary 68.4. All right, and that's really all I have for you in that lesson. A lot of stuff going on there, but it's a lot of stuff that's kind of review for you. You should remember most of that from grade school, but there was a few new things kind of plugged in there. So hopefully you paid attention. If you missed anything, make sure to slide it back, watch it again. We'll see you later. Have a good one. Bye-bye.